This is a presentation for the machine learning course. The title of our project is Mastering Dots and Boxes by Self-Play with Reinforcement Learning. First, I want to briefly introduce what is Dots and Boxes. It is a two-player strategy game with simple rules, which can be played with just paper and pencil. Basically, this game starts with some dots and grids, and the players in turn connect two adjacent points. The player who draws the fourth edge occupies this box and must perform an additional move. Game ends after all lines on the grid are drawn. At the end of the game, who owns the most boxes wins the game. Here is a simple demo with a 2x2 game board. 4 boxes in total. Red player gets 1 box and the blue player gets 3 boxes. So blue player wins this game. Although the rule of dots and boxes is simple, to master this game with computer can be very challenging. The search space of dots and boxes can be huge. For example, with a 4x4 game board, which have 40 edges, the number of all possible states is 2 to the power of 40. Also, we can only know the result of the game after all edges are selected. This makes a general search algorithm impracticable. Not to mention the strategies of dots and boxes can be very complicated. Until now, the best known solver can only solve 4x5 dots and boxes. In this project, we will use AlphaZero to master this game. You are probably already familiar with AlphaGo. It's the first program to defeat a professional human Go player. And in AlphaGo Zero, AlphaGo becomes its own teacher. AlphaGo Zero can achieve superhuman performance without any human data or domain knowledge. As you can see, AlphaGo Zero takes only 40 days to become the best Go player in the world. It does this entirely from self-play. AlphaZero is a more general algorithm that not only can be used to master Go, but also can be used to master chess and shogi, the Japanese chess. Then I will introduce what is self-play reinforcement learning in AlphaGo Zero. Self-play means the program will play a game against itself. In each position, a Monte Carlo tree search is executed using the latest neural network, and all moves are selected according to the search probabilities computed by the MCTS. So basically, self-play is one MCTS plays against another MCTS, and both of them were using the neural network to evaluate their movements. Now we come to the neural network in AlphaGo Zero. The neural network takes the raw board position as its input, and output both a probability distribution of moves and the probability of current player winning. This will be used in MCTS to choose a good move for both players. To train the neural network, we can simply update parameters so as to maximize the similarity of the policy vector to the search probabilities computed by MCTS, and also to minimize the error between the predicated winner and the real game winner. The new parameters computed will be used in the next iteration in MCTS for self-planning. Now I will explain how the Monte Carlo tree search works. Monte Carlo tree search is a heuristic search algorithm for some kinds of decision processes, most notably those employed in gameplay. In MCTS, each tree node represents a possible move. Different from other algorithms, MCTS focus on the most promising moves. It expands the search tree based on random sampling. It selects moves by applying many playouts, and in each playout, the game is played out at random. The final game result of each playout is then used to weight the nodes in the game tree, so that better nodes are more likely to be chosen. The MCTS consists of 4 steps: selection, expansion, simulation, and backpropagation. I will introduce these 4 steps one by one. First, in the selection step, we try to select good child nodes that represent states leading to better overall outcome. More specifically, we will choose a child with the highest UCB value. UCB represents for upper confidence bound. In this equation, Vi is the average reward of the subtree, N is the number of times the parent node has been visited, and Ni is the number of the child node I has been visited. This equation shows that we should not only focus on the child with highest reward, but also try with nodes that hardly been visited before. In the second step, we simply create one or more child nodes for a non-terminal node. In the simulation step, we run a simulated playout until the terminal. The policy used in playout can be as simple as choosing uniform random moves. It's provable that the MCTS will converge to optimal moves if we try it many times. And the last step is backpropagation. In this step, we update the current move sequence with the simulation result. So these are all things we need to build our AlphaZero for dots and boxes. But before evaluating our implementation, we also need to find a benchmark. We don't have much computer resources, and the dots and boxes is too complicated to be solved by pure MCTS. So we need to implement a reasonably intelligent algorithm as the benchmark player. I will first give some observations about dots and boxes. The first one is that players will avoid to draw the third edge of a box, because if a player draws the third edge, the opponent will take this box by drawing the fourth edge. Another observation is that this game will reach a balance point that all boxes have exactly 2 edges, based on the previous observation. Also, we observed that it is easy to find an optimal policy start from the balance point. In fact, it is possible to design a deterministic algorithm to get optimal moves after the balance point. Based on above observations, we implemented the benchmark player. It will try to have advantages in the whole game, even at the expense of sacrificing some boxes. Actually, we can prove that our benchmark player can achieve optimal policy in the game after balance point. To master dots and boxes, we trained our AlphaZero model and compared it with the benchmark player. After training for 3,000 rounds, we got a model which can achieve around 60 to 70% winning ratio against the benchmark player. Here is an example. You can take a look if you are interested. That's all our presentation. Thanks for listening.
Now let me show you how AlphaZero player work. In this round, AlphaZero player is the second player.